So it's a real honor to be here to be able to share with you the results from my early release science program, Ice Age, about ices in the star formation process. Before I go further, I just want to acknowledge that this is a real team effort, and there's a lot of people in the room who are actually members of the Ice Age collaboration. And the work I'm about to show is a testament to the legacy of laboratory astrophysics experiments done by our co-PI, Professor Harold Lennertz, who unfortunately passed away in December. So I'll be brief about this because we've seen really great introductions so far. A lot of the elements that are important for the life in the universe and also exoplanet atmospheres are carbon, hydrogen, oxygen, nitrogen, and sulfur. They're heavily depleted on Earth, really mostly only in a skin on the surface. And they may have been delivered to Earth by icy planetesimals early in Earth's formation history. And these planetesimals are like Comet 67P may have delivered both simple ices as well as larger complex organic molecules and perhaps refractory species like the PAHs or iron sulfide. So we want to understand how these elements get into other planets. We need to understand how these molecules and solids formed. Now, comets are the end product of the star formation sequence, which goes back all the way to molecular clouds, dense cold molecular clouds. And this is where the ice component of the solids forms at temperatures of around 10 Kelvin. So we need to study where the ices form in molecular clouds in order to understand what gets into planets. However, we also know that these ices get heated up as they infall from molecular clouds onto protoplanetary disks through the protostellar envelope stage. So we really need to understand each stage of star formation in order to answer this question about planetary compositions. So our big observational goals are characterizing what the content of the clouds, determining how these ices are chemically altered in the protostellar phase, and determining which cloud ices are inherited by protoplanetary disks. The second topic will be covered in Yao-Lun's talk right after me, so I'll focus on the first topic, and if I have time, the third. All right, so to answer all these questions, Ice Age is looking at a very compact region in the Chameleon-1 star-forming molecular cloud, where serendipitously, we have all of these stages of star formation at once, ranging from the prestellar core to two protostars to an edge-on protoplanetary disk. Now, we observed all of these stages with different modes on JWST. So for the cloud and the molecular, the prestellar core, we used a combination of near-cam wide field spectroscopy and supplemented that for 2 lines of sight with near-spec fixed slit mode and MIRI LRS. Then for the protostar and the disk, which have physical structure, we mapped those using the IFU modes of near-spec and also MIRI. Now I'm going to zoom in on this central region here. This is what we saw with IRAC and Herschel, IRAC in green, Herschel in red. And this is what we see with JWST's NearCam. And it's just spectacular. So you can see all of the targets that I mentioned before, as well as a large number of galactic or extragalactic interlopers. And we can even see a little jet coming out from this hidden class 0 protostar. So the data are really fantastic. Now I'm going to focus on the one of the background stars to show you some of the ice results. So the ices show up in absorption features against the continuum of the background star stellar spectrum. And we see all of the main ice species like water, CO, CO2, methane, and ammonia, as well as silicates. Now, this is great for determining elemental budgets, but of course, the real new science is going to be in the weaker features that we see. So if we focus on some of those weaker features here, the high sensitivity that we get with a signal to noise of between 250 and 400 over this whole region allows us to detect for the first time in molecular clouds the OCS molecule, which is the first sulfur detection in molecular clouds. And interestingly, we do not detect H2S, which is supposed to be the primary carrier for sulfur in ices and clouds. And we also have an upper limit for SO2. I just want to point out for the quality of this data, those wiggles that you see around the OCS feature, those aren't noise. Those are the CO fundamental gas phase absorption lines in the stellar photosphere of the background star. That's how good the data quality is. So we can use the ices that we detect and calculate abundances for them, doing a detailed fit to the whole spectrum. The species that are highlighted in magenta are new for molecular clouds. And we can get these elemental budgets for each of the different elements. And the thing to note here is that ices make up at most 50% of the elemental budgets for say, carbon and oxygen. But for nitrogen and sulfur, we're really only seeing a small part of the total elemental budget, which means that the refractory species are playing a very important role in the composition of the solids and going onto planets. One important thing to note here, and I'll get back to this hopefully at the end of the talk, we don't see any signs of PAHs in this molecular cloud, despite the fact that 51% of the carbon needs to be in some kind of refractory species. We looked for it, we don't see them either in absorption or emission. So what else can we do with our really awesome high signal to noise data? Well, we can now look at the chemical environment in which these ices formed if we focus on a set of these other features. So here is a very simplified view of how we thought that ices formed on grains before. You first have your naked grain in the ISM, then you form a water-rich layer on top of it, then you form a CO-rich layer on top of that, and eventually with catastrophic CO freeze-out, you're able to form a methanol-rich layer on top of the CO layer. And at first, when we look at the ice profiles that we see, now that we have good spectral resolution with GWST, we see something that sort of confirms this view at first. We appear to see methanol mixed with CO, which suggests we're viewing this last stage. But then we also see, if we look at the methanol feature itself, we see that methanol is also mixed with water. There's a component with CO, a component with water, which suggests that methanol forms by a different route than we thought initially at earlier stages in a water-rich stage, as well as the route we thought at later stages with CO. And it's not just methanol that does this. We can also look at other complex organic molecules. And you can see that there are some very weak features here around 7.4 microns that are compared with laboratory spectra in the panel on the right. And these are signatures of ethanol and acetaldehyde, essentially. And this is something that Yalan will show additional spectra of in his talk. So all of these laboratory data were fit with complex organic molecules that are in a water-rich matrix as well. So this is suggesting that they formed early in that stage. More confirmation that we see water mixed with a lot of other ice species comes from this dangling OH feature that we also detect. So there's a main water feature, the OH stretch at 3 microns. And there's this much weaker feature, a set of 2 features right next to it. And these can either be created when you have mixed ices with water and that OH bond is not connected to anything else, or when you have a pore in the ice and the OH is dangling out into the pore. So we actually detect, using NIRChem's wide field slit spectrograph, this feature along 8 different lines of sight. And you can see in the stacked spectrum that we have there that it's a reliable detection. So we are seeing some kind of mixed water ice environment, potentially porous as well. We can't eliminate that possibility. One other interesting thing that we can get from the profiles is that we're definitely seeing that grains have grown in the molecular cloud relative to the ISM. So this is in black the data, and in colors 3 different grain size distributions with 3 different maximum grain sizes. And the shape of the CO2 feature is altered so that you get a distortion with blue shifted emission, red shifted absorption when you have larger grains. So when we do a detailed fit to these data by Emmanuel Dartois in a paper that came out recently, they get a maximum grain size of 0.9 microns. And this is consistent with what we would get for dynamical growth models of grains in molecular clouds. So in summary, for the cloud itself, we were able to characterize the ices in the cloud. We see that sulfur-bearing species are underabundant. We don't have PAHs in the cloud ice. Refractory species are important. Chemically diverse ice mixtures are present. We also see that there are complex organic molecules that must have formed early in the water-rich phase. The implications for planet formation are that the refractories could enhance the Chon's abundances in planet feeding zones, that these mixed ices may enable some of the more volatile ice species to survive and fall onto the protoplanetary disk during the hot protostellar stage, and that we have larger grains which should have less surface for chemical reactions and absorb less radiation, which may enable them to survive longer. So then the question is, when we look at disks, what do we see that they've inherited from their molecular crowd? This is a complete near-spec and MIRI spectrum of the disk in the Ice Age program. And we can see a number of different features. It's being worked on by my PhD student, Arjun Sturm, so it's still in progress. But we see a number of gas phase emission lines, which I think Colette will talk about in her talk. We also see pH emission at 11 microns, as well as the ice features, which we expected. And Arjun's able to get a really great fit for this using both ices in the disk as well as pH emission that's localized in the disk. And I want to emphasize this is in the disk itself, not in the background, because he's getting a really good fit the feature. So as a small interlude, I'm also the PI of another program which recently published some additional spatially resolved observation of pHs. So Nicole Runlantham just posted this on arXiv. It's under review. And you can see that she detects a really nice disk wind in molecular hydrogen, this nice hourglass shape, as well as spatially resolved pH features in this disk. It's an M2 T-Tauri star, and it doesn't have external radiation. So this is confirming that pHs do exist in such low mass systems. So we are seeing the refractory carbon in these systems. So if we turn back to the Ice Age disk, we can use the observed spectrum to extract a map of, say, the water and CO and CO2 in this disk. And we note that the optical depths, although they appear small, are actually very similar to each other. And this is suggesting that the disk is locally saturated, or the ices are locally saturated in the disk. And we need radiative transfer models in order to extract abundances from the optical depths and column densities because they're not in a linear regime. So when Arjun runs radiative transfer models for this, he finds that the water abundances are enhanced by about a factor of 5 relative to the interstellar medium, which is important for planet formation. We can also take that spatial distribution and look at the vertical distribution of ices. Interestingly, even though CO sublimates at about 20 Kelvin as opposed to like 150 Kelvin for water, we see that CO is actually still quite abundant further up in the disk when we would have expected it to drop down to a very low level because it's sublimated. So this is one question is, could this CO ice actually be trapped in either water or the CO2 ice matrix and be carried up into the disk because of this and survive because of this, erasing the vertical CO snow line? This is something that has been seen in laboratory data, including some of this work from Karin's group. So one of our collaborators on the team, Jenny Bergner, took a more detailed look into this. So she took laboratory data from mixed ices and combined them with a radiative transfer model to study how they impacted the line profiles. So if you have a layered disk or a layered ice grain like this, you get very sharp peaked profiles, particularly for CO and CO2. However, if you have a thoroughly mixed grain, then you get very broad features for CO and CO2. So when she looks at our actual data and does a more detailed fit, she finds that it's not possible to have pure CO anywhere in the grain. The CO must be mixed preferentially with CO2 in order to reproduce CO profile. And this she also finds again that the ice abundance is about now a factor of 3 higher than the ISM. And this has a lot of implications for C/O ratios and snow lines in protoplanetary disks. So she ran this through some of her models and found that the ice C/O ratio, when you include the mixture, will partially erase the CO snow line. And this is a comparison for the solid C/O ratio from what Karin had in her seminal 2011 work relative to what we find now with the mixed ices. So it could have a large impact on planetary cores that form in different parts of this disk. So the bottom line is that planetary COVR ratios are very tricky to interpret in the context of disks with mixed ices. So this is the net conclusions for this section. So disk ice maps are impossible without accurate radiative transfer modeling. And we have a mechanism by which carbon-rich ices survive closer to the star to produce more carbon-rich planets closer in, which was, I think, was one of the things that was coming out of the discussion yesterday. So I'll leave this up as my conclusions, and thank you for your time.